Going to state and prove the binomial theorem. So remember what the binomial theorem is. So for n, an integer greater than or equal to 1, if you have x plus y raised to the n, so it's our binomial here, x plus y, that expands to the summation, we'll say of k equals 0 up to n choose k, x to the k, y to the n minus k. Okay, so that's the binomial theorem that allows us to expand a binomial for any integer n greater than or equal to 1. And we want to do the proof of this, but before we do, we need two identities. So let's write them down here. So n choose r, so remember that's out of n objects, we're choosing all the groups of size r. Well, this is equal to n choose n minus r as well. And let's think through that. So if we choose a group of size r and this whole thing has n, well then we're also choosing at the same time a group of size the rest, which would be n minus r. So for every group of r, there's a group that wasn't counted or wasn't included, which is a group of size n minus r. All right, the next one is this. So n choose r is also equal to n minus 1 choose r minus 1 plus n minus 1 choose r. And the way we're going to think about this is, so let's say our group, our elements, our n elements are labeled 1, 2, 3, up to n. So that's the set that we're pulling from. And if we pull a group of a group of r, we're going to split it up into two disjoint sets. So the ones that contain 1 and the ones that don't. So all groups of size r either contain 1 or they don't. So if I want to count the number of groups of size r that contain 1, that means 1 is in the group, and I need to choose the other elements of the group of size r. So that's going to be n minus 1, because we've already got 1 in the group, and we have one less member to choose from because we're going to choose the rest, r minus 1 of them. So if our group was size 4 and 1's in there, 1 is accounted for, we need to choose the other 3. Okay, plus now all groups of size r that don't contain 1, which means we don't include this. So we have n minus 1 to choose from, and we need to choose all r elements. So that's all groups of size r, right? The ones that contain 1 and the ones that don't. Useful. All right, let's do our proof. We're going to do a proof by induction. Which is often what we do when we're proving things with integers greater than or equal to 1. All right, so our base case, p of 1. So if we let's rephrase this. So we're going to let p of n be the statement, the binomial theorem statement, okay, that x plus y raised to the n is equal to the summation of k equals 0 up to n choose k, x to the k, y to the n minus k. You can actually flip those if you wanted to. All right, so that's the statement. We want to prove that this statement is true for all n. So our base case, so p of 1, well, x plus y to the 1, that's our left-hand side. All right, so that's the left-hand side of this statement. The right-hand side would be, we're going to go from k equals 0 up to 1 choose k, x to the k, y to the 1 minus k. And that expands to, well, k equals 0, so 1 choose 0, x to the 0, y to the 1, plus 1 choose 1, x to the 1, y to the 0. 1 choose 0 is just 1, x to the 0 is just 1, so that's really y, plus 1 choose 1 is 1, x, y to the 0 is 1. So here, the left-hand side does, in fact, equal the right-hand side. So our base case, the statement is satisfied for n equals to 1. Okay, so now we're ready to make our deductive hypothesis. So we're going to say, assume the statement is true for some n minus 1. So assume P of n minus 1 for some n greater than 1. Okay, so what that assumption is telling us that x plus y to the n minus 1 is equal to, we're assuming this is true, k equals to 0 up to n minus 1, n minus 1, choose k, x to the k, y to the n minus 1, minus k. Okay, so we now need to show it's true for the next element, which would be n. All right, so let's see what this left-hand side, let's switch to green. For our left-hand side, x plus y to the n, we know that we can write this as x plus y times x plus y to the n minus 1. Just pull off one factor of x plus y. Here's where we're going to use our assumption. So this is equal to x plus y times the summation, k equals 0 up to n minus 1. N minus 1, choose k, x to the k, y to the n minus 1 minus k. We're just using what we assumed to be true. All right, so we're now going to take this coefficient and distribute it to those two terms. Just distribute it out. So we should have x times this summation, x, k equals 0 to n minus 1, n minus 1, choose k, x to the k, y to the n minus 1 minus k. Plus, now we got to distribute the y, same thing. Let me do it really fast. K, x to the k, y to the n minus 1 minus k. We're going to say k equals 0 up to n minus 1. Pause if you need to catch up with following what's going on, and don't hit play until you know why we have the statement that we have. Okay, we're now going to shove the x in and the y in to its respective pieces. So this should be, I'm moving it over a little bit, k equals 0 up to n minus 1, n minus 1, choose k, x to the k plus 1, y stays put, n minus 1 minus k, plus k equals 0 up to n minus 1, n minus 1, choose k, whew, it's tedious, x to the k, y, we're going to add one more y, so it's going to become just n minus k, right, because we added the 1. Now we're going to do a favorite thing we do in proofs by induction sometimes, and we did in calculus, is we're going to do a change of index, okay? So, and we're going to do it separately for different ones. As long as it generates the same sum, we can rename our index anything. Just make sure everything adjusts. Okay, so in this one, we're going to let I be equal to k plus 1, or k is equal to I minus 1. Over here, we're going to leave it fixed. We're going to call it I, but we're going to just let that stay put. Okay, let's see how the left changes. So when k is 0, I is 1. So this sum becomes, back to green, oops, that's not green, becomes I equals 1 up to n. Okay? And then this is still n minus 1, but instead of choose k, it's choose I minus 1. X to the I, y to the n minus 1 minus k, so that k is I minus 1, right? So minus I minus 1 is I plus minus I plus 1. Woo! So this becomes just n minus I. Okay? And we're going to rename these things. I equals 0 up to n minus 1. That's not changing. N minus 1 chooses I. We're just replacing it with i's instead of k's. Okay? All right. Oops. Okay, next we're going to pull off the nth term here and the 0th term there, because we want sums to be starting, we want to be able to combine these sums, and so we need them to have the same index values. So we're going to pull off the nth term. So the nth term is when I is equal to n. Okay, so we're going to replace all of our i's with n for that term. So we should have, yes, n minus 1, choose I is equal to n here, n minus 1, x to the n, y to the n minus n, y to the 0. So that's just the nth term, which means I'm left with I equals 1 up to n minus 1, n minus 1, choose I minus 1, x to the I, y to the n minus I. Plus, now we're going to pull off the 0th term on the other side. So I'm going to write this first, starting at 1, n minus 1, n minus 1, choose I, x to the I, y to the n minus I, and then take off that 0th term that we eliminated here. So when I is equal to 0, we have, oops, I'm going to change it to pink, n minus 1, choose 0, x to the 0, y to the n. Okay, so now we're going to use that identity. Well, first we're going to combine these. So notice that I have the same index, I equals 1 up to n minus 1 on both sums, so I can group them together. And notice also that my x and y's are raised to the same power. It's just I have different coefficients. So what does that look like? It becomes the sum, I equals 1 to n minus 1. I can factor this out. So x to the I, y to the n minus I. And then what's left inside is this first one, n minus 1, choose I minus 1, plus n minus 1, choose I. And then these pink terms. And so this last pink term right here is just y to the n, and this first term right here was x to the n. Here's that identity. So that's like the groups of size I, ones that contain 1 and ones that don't. So we know that this becomes n choose I instead of r. N choose I. Okay, let me rewrite that over here and in front. So what I have here is I equals 1 up to n minus 1. Let's put our coefficient here. Our coefficient is n choose I. And we have x to the I, y to the n minus I. And then we have this x to the n and this y to the n. Okay? So if we put that x to the n back, which we knew how it was, it's going to bring back that top term. And if we put that back in, remember how we got it? It was when I was equal to 0. So it's just going to bring this thing down to 0. So it's going to be I equals 0 up to n. N choose I, x to the I, y to the n minus I, which is this statement right there. So we showed the statement was true for 1. We assumed it was true for n minus 1, and we're able to conclude that if it were true for n minus 1, it is true for n, which is all we need to do to prove by induction. Fun.